Every blockchain promise you've heard, immutability, censorship resistance, trustless consensus, comes down to a small set of math problems. In this module, we'll unpack those cryptographic building blocks, see where they live in real stacks, and show how quantum risk directly threatens them. Verifiable trust is really an invisible cryptographic layer under everything. Hash functions, digital signatures, and public-private key pairs are the core primitives. Most current trust architectures assume, as long as these math problems stay hard, our identities, transactions, and histories remain safe. AI and quantum computing directly pressure that assumption. When you design for verifiable trust, think in terms of three pillars. First, integrity, the immutable past. Hashes and Merkle trees don't prove who did something. They prove the data and history haven't been altered. Second, authenticity, the verifiable present. Digital signatures bind actions to identities and intent. Third, access and control, the human interface. Key management and multi-sig decide who can actually move assets or change state. Any serious risk analysis has to cover all three. Hash functions are the first pillar of verifiable trust. Think of them as digital fingerprints. You feed in any file or message and get a short, fixed-length identifier. The same input always gives the same output, but even a one-bit change completely scrambles the result. Crucially, they're one-way. From the hash alone, you can't reconstruct the original data. Hash chains are what make a blockchain's history tamper-evident. Each block contains a hash of the previous block's contents. If an attacker changes anything in an old block, its hash changes, and every later block pointing to it becomes invalid. To hide that change, they'd need to recompute the proof of work or consensus for all subsequent blocks. So immutability is enforced economically by making rewrites prohibitively expensive. Merkle trees let you prove that a specific transaction is in a block without reading the whole block or chain. Each leaf is a transaction hash. Parents are hashes of their children, all the way up to a single root stored in the block header. To verify one transaction, you only need the hashes along its path to the root. That short Merkle proof detects any tampering and scales to millions of transactions. Commitment schemes are like putting your value in a locked safe in public. In the commit phase, you lock in a choice or value so you can't change it later. That's the binding property. At the same time, nobody can see what you chose yet, which gives you hiding. In the reveal phase, you publish the opening key. Anyone can now verify you knew this value earlier. This underpins sealed bid auctions, fair voting, and front-running resistance. In modern blockchain systems, your identity isn't an account row in a database. It's the output of a one-way mathematical function. You hold a private key that must stay secret. From that private key, a public key or address is derived. Others see and use only the public side, but can't feasibly reverse it to recover your secret. So control flows from the private key, while recognizability and routing happen through the public key. Digital signatures turn "somebody sent this" into "this specific key owner approved this exact message." You combine the message with your private key to produce a signature. Anyone with your public key can verify that signature against the message. If it checks out, they know two things: the message wasn't altered, and the private key holder authorized it. That yields non-repudiation. The signer can't later credibly deny the action. Key management is where human behavior collides with cryptography. Hot storage keeps keys on internet-connected devices or services. It's ideal for frequent transactions, automation, or experimentation, but every added convenience expands the attack surface. Cold storage moves keys offline, hardware wallets, air-gapped machines, or even paper. It's slower and operationally painful, yet dramatically reduces remote compromise. Robust architectures blend both. Minimal funds hot, strategic reserves cold, with clear policies for moving value between them. Multi-sig and threshold schemes turn access control into a small consensus protocol. Instead of one private key controlling critical assets, several parties hold independent keys, and a predefined subset must agree before any action executes. This removes a single point of failure and is essential for securing corporate treasuries, institutional custody, and DAO governance decisions. Every trust architecture sits on a spectrum between maximum security and maximum usability. On the security side, you get air-gapped keys, multi-sig and slow, carefully controlled changes. That reduces catastrophic loss, but it also kills velocity and user adoption. On the usability side, you get biometrics, social recovery, and one-click flows, great for growth, but easy to misconfigure or abuse. Your job is not to maximize either extreme, but to deliberately design and continuously monitor the balance. Quantum computers don't just make things faster. They break a core assumption of today's public key cryptography. Shor's algorithm can derive private keys from many widely used public keys. That means signatures, identities, and access controls built on RSA or elliptic curves can be forged, even retroactively, once strong quantum machines exist. Hash-based integrity largely survives. Authenticity and access do not. Harvest now, decrypt later is a timing problem, not a math problem. Attackers don't need quantum computers today. They just need to copy encrypted data and wait. For ordinary databases, that's bad. For blockchains, it's worse, because you can't rotate history. Every vulnerable signature, every encrypted payload you anchor on chain becomes a permanent liability. So post-quantum planning isn't optional. It's about protecting the future by changing what you record today. Here's the big picture to carry forward. Integrity comes from tamper-evident data structures. Identity comes from strong, well-managed keys. Control comes from governance and multi-party authorization, not single admins. And future safety demands post-quantum readiness. Modern trust is engineered, measurable, and cryptographically provable.